All right, so now we're going to talk about the domain of a function. So functions that we're going to be using in calculus, things like rational functions. So what is a rational function? It's a function that is a polynomial divided by another polynomial. So let's say something like x squared minus 2x plus 3 all over x. Let's do x squared minus 4, something easy to factor. I'm going to think more than I need to. Let's just start with something very simple like this. And so we want to find out what is the domain of this function, the largest domain you could define for this specific function. Excuse me. So what you would do is you would ask yourself, when is this function undefined? What can go wrong on this function? And what can go wrong is that you may be dividing by 0. That is the first thing you would notice. So you say, well, what happens? How can that happen? Well, that's when the denominator becomes 0. Well, and then you realize that this can be factored as x minus 2, x plus 2, because it's a difference of squares equals 0. And from that, let me change markers real quick. And from that, you get 2 possible points. One is when x is equal to 2, and when x is equal to negative 2, by setting each one of these factors equals to 0. Now, word of caution, the way we're solving it, we are factoring and setting a product equal to 0. When you have two numbers that multiply to 0, then you know that at least one of them will be 0. So that's how we say then x minus 2 equals 0 and x plus 2 equals 0. But then often you find that some people, not you of course because you're watching my video, but let's say that you would get something like this. And so people make the mistake, they say, well, then x minus 2 equals to 1 and something else. No, that doesn't work for any number but 0. Because 0, you know, the only way you can two numbers can multiply to 0 is if one of them is 0. So be very careful with that. That's a very typical mistake. So what does this tell us now? What this tells us is that these two numbers have to be excluded from the domain of this function. Why? Because when you plug them in, you get something that is undefined. So you're going to say that the domain of this function, and we could just summarize it as d of f, is simply going to be the set. I'm going to write it in set notation first, is the set of all x's such that, and I'm going to assume x's are already real numbers, that x cannot be equal to 2 and x cannot be equal to negative 2. So those two are going to be excluded. In interval notation, as you know, you start going from negative infinity until you find the first of the two, which is going to be from left to right, negative 2. You leave it open so you don't include it. Union, you start from that same number. You already excluded that negative 2. You go to the next one, if there's any. Open, so you can exclude it. And then you go from that point to the next one, but there's no next one, so the next is going out to positive infinity. So in interval notation gives you that. You could also look at the graph from negative 2, 2, and this interval corresponds to this part. This interval corresponds to this part. And lastly, this interval corresponds to this part. So if I ask you for the domain of a function, there you have it. And for calculus, it's going to be extremely important for us to find domains. So please be mindful and practice those skills to find domains of functions. So what other functions could we be interested in? Well, for business calculus, which is what this video is aimed for, we're going to be doing polynomial functions, rational functions, exponentials, and logarithms. You guys are not going to see trigonometric functions, which may be great for you, makes me a little bit sad, but let's then go ahead and talk about exponential and logarithms. For any rational function, you're going to be doing this same procedure. Finding the domain will be setting your denominator equal to 0, and then all those roots of the polynomials, or the denominator rather, will give you the points to exclude from the domain. All right, so let's go ahead and look at what happens with exponentials and logarithmic functions real quick. And so I'm going to erase, and I'll be right back. All right, so let's take a look at two examples, one with an exponential and the other with a logarithm. I'll start with the exponential. The domain of an exponential function is the entire real line. This one is just a shift, doesn't matter. X plus 2 can be any real number, therefore x can be any real number. So the domain of this function, when you have exponentials, you don't have to be too careful. Unless the exponent is something that has a radical or a rational function, then sure. But in this case, there's nothing, it's just a linear function in the exponent. So the domain of g is the entire real line that you can write from negative infinity to infinity, or you can just write it with this blackboard bold R. Done. All right, that was easy. By the way, I also lied to you. I just realized right now. There's also another type of function we'll be interested in. Radicals. We'll talk about those in a second. So now let's take a look at the expression here, the logarithm. So to remind you, the graph of the logarithm, just straight up logarithm, has an asymptote at 0 and is undefined to the left. So it's only defined when the argument of the logarithm is strictly positive. So what you're going to do is you're going to be interested in finding the domain, or the set rather, where the argument of the logarithm is strictly positive. So what is this? Well, this is you're going to graph your function and you want to see where it's positive. So the graph of y equals x squared minus 4, we do it in the same way we did before, and it has two intercepts. Oh, I didn't talk about intercepts yet, but I'm sure you talked about it a lot in college algebra or pre-calculus. But in this case, they're going to be negative 2 and positive 2. So this is the graph of y equals x squared minus 4. So I want x squared minus 4, so in this case our y, to be positive. Well, where is the y positive? Well, it'd be to the left of negative 2, because you see the y's here are positive. Then they turn into negative once you pass that point. And then they're going to be to the right of, and I did this should be open, sorry, it's not a bracket, it's a parenthesis, sorry. And then it should be to the right of positive 2, because above or past the positive 2, the graph is above the x-axis. So in this case, my domain, which is the solution to this linear or quadratic inequality rather, is going to be the interval from negative infinity to negative 2 union 2 to infinity. So I'm excluding that interval from negative 2 to 2. So I have to exclude that. All right, so that would be the domain for this function. It would be just where the argument of the logarithm is strictly positive. So that's how you do your domains for logarithms. You grab the argument, make sure that that's strictly positive. Now, what about your radicals? Well, if it's an even radical, if it's not a cubic roots have no problem, but square root, for example, does have a problem with negatives. And so you will require that x plus 4 be greater or equal than 0. So that's going to be your linear inequality. This one is easy to solve algebraically, so you just say x is greater or equal to negative 4. And what that corresponds to is the interval starting at negative 4, close because I have equality here is allowed, all the way to infinity because I'm going to the right. I want the greater or equal part. And so x better be to the right of negative 4, meaning it's going to be larger. So I'm going to grab this whole interval from negative 4 out to infinity. Any of these x's is good enough. All right, so that's how you would do your domain. So the next question is, how do you find intercepts? That's another thing we will be interested in doing, finding intercepts for a function. So I'm going to erase here, and then I'll come right back. All right, so I decided to keep the same function so we can look at intercepts. So you're going to be interested in x-intercepts. And what do those represent? Those represent the points where the graph touches the x-axis. But what does that mean? That means that y is equal to 0 on that line. The x-axis is the line y equals to 0. So what I'm going to do when I want to find x-intercepts, I'm going to set y equals to 0. In this case, f of x is y. So I'm going to do 0 equals the natural log of x squared minus 4. And now you have to solve that equation. And to solve that equation, you do e to the power of 0 equals e to the power of the natural log. Why? Because e and the natural log are inverse functions, therefore they cancel. Hand waving there. So e to the 0 is going to be equal to e to the natural log of x squared minus 4. E to the 0, we know that any real number not equal to 0 to the 0 is going to be 1. And in the limit sense, we'll talk about 0 to a 0. And then e to the natural log is going to be x squared minus 4. So what you would do now to solve, you can add 4 on both sides and get x squared equals 5. And you take your plus minus square root, and you get that your intercepts are going to be of the form plus minus root of 5, comma 0. Oops. Comma 0. And that gives me my x-intercepts. Now, if you want to do y-intercept, why do I say y-intercept? Well, because that is going to be the point where the line crosses, the graph crosses the y-axis, but that is going to be when x is equal to 0. So that should be the value that the function is getting when x is equal to 0. And that value is going to be unique if there exists. So in this case, I would set x equals to 0, and my function is not going to have 1 because f of 0, as we stated before, the domain was from negative infinity to negative 2, and then from 2 to infinity. F of 0 is undefined. So this graph simply never touches the y-axis, which is fine. But it does touch the x-axis 2 times. So that's how you find your x and y intercepts. My example for the y-intercept was not very nice, just because I chose a function that didn't have one, but the procedure is always the same. So in the next video, we'll be talking about limits. That's the first and most crucial concept of calculus. So thank you for watching, and I'll see you in the next one.